I would like to follow up our class discussion of local linearization by talking about two ways that you can use your local linearizations. And the first, let me remind you that our local linearization is that for x's close to c, f of x is approximately equal to the tangent line. And so our plan is to use this local linearization to estimate f of x, or to find zeros, that is to solve the equation f of x equals 0. Both of these right here are going to be estimated values, not exact values. That's okay. So to get the spirit of this, I want to consider this question. Imagine for a moment that you're stuck on a desert island without a calculator. And to get off that desert island, what you need to do is to construct a helicopter out of coconuts and palm trees. And for that purpose, you need the square root of 4.15. Work with me here. This is a pretend scenario. Now, I don't know the square root of 4.15, and I'm guessing that you do not either unless you have a calculator. However, there is an x value close to 4.15 that you do know the square root of. What is that x value? Well, of course, that x value, which we will call c, is 4. We know that the square root of 4 is 2. So our plan is going to be to construct the local linearization, which I'm going to abbreviate as loclin, the local linearization of the function f of x equals the square root of x at c equals 4. And then I'm going to use that local linearization to estimate values of f of x, specifically to estimate the value of f of 4.15. Well, the local linearization is simply the tangent line. And so we know how to do that already. We know that it's going to be f of 4 plus f prime of 4 times x minus 4. And so, since f of x is the square root of x, we need also to compute f prime of x, which is 1 over 2 root x. And this allows me to immediately find the values. F of 4 is 2, and f prime of 4 is equal to 1/4. Plugging in here, I get 2 plus 1/4 of x minus 4. This is the local linearization, and for x's that are close to 4, it is a good approximation of the square root of x. Please notice that I have replaced my square root function that I can't evaluate with a nice straight line that I can. And so the answer to my question is that f of 4.15 is approximately equal to 2 plus 1/4 of 4.15 minus 4. And that simplifies to 2 plus 1/4 of 0.15. And we can do this in our heads. That's 0.15 divided by 4 is the same as 0.0375. And lo and behold, I've come up with a good estimate for the square root of 4.15. How good is that estimate? Well, we make our helicopter, we get off the island, we get back to civilized technology, and we ask, what is the square root of 4.15 anyway? How well did we do it? And when you find the square root of 4.15, it turns out to be 2.03715. So the actual value to 5 places is this guy right here. That's not very far away from the 2.0375 that we calculated. We could give an idea of how good our estimate is by computing the error. And the error is going to be the actual minus the estimated value. And we'll take the absolute value of that difference because we're only interested in the size and not the direction of the error. So our absolute error was only 0.0003, and we did that computation all with pencil and paper, never having to appeal to the calculator. That's really powerful. And in fact, in the wild, I do these kinds of tangent line estimations or local linearization estimations on a frequent basis. And so do computers, because computers, obviously, don't have access to another computer to do the calculations for them. They are the computer. And so the way that they do a lot of these computations is with local linearization. I want now to consider a second question. And that is to estimate the zero of f of x equals x cubed plus x plus 1. In other words, I want to solve the equation x cubed plus x plus 1 is equal to 0. Well, I don't know. So I start playing around a little bit with numbers. Just start plugging them in. And I plug in x equals -1, and I plug in x equals 0, and I might plug in some other values to get a feel for it. But when I plug in x equals -1, I get -1 cubed plus -1 plus 1 is equal to -1. And when I plug in x equals 0, I get 0 plus 0 plus 1 equals 1. And so I notice that f of -1 is less than 0, and f of 0 is +1, which is greater than 0. And a little bell from last chapter goes off in my head, and that bell is the intermediate value theorem, which guarantees me that since f is a continuous function, how do I know it's continuous? It's a polynomial. Since f is a continuous function, therefore, there must be a c between my two x values such that f of c is equal to any value between my two y values, specifically 0. So I am guaranteed that there is a 0 somewhere between -1 and 0. And you remember that in the last chapter, we took our function f of x that looked like this, and we found our 0 by bisection, by taking the interval from -1 to 0 and cutting it in half each time. Well, we now are going to use our tangent line to do it by a much faster method. What we're going to do is to construct a local linearization at one of these points. Let me just pick -1. I'm going to construct the local linearization at c equals -1, and then I'm going to use that value to estimate a solution to the equation, and it's very easy. Here's how we do it. First of all, we construct the local linearization. F of x is approximately equal to f of -1 plus f prime of -1 times x minus -1, which is equal to, we already found -1 for f of -1. I need an expression for f prime, and here it is. F prime of x is equal to 3x squared plus 1, and therefore f prime of -1 is equal to 4. And so there is my local linearization. Let me keep the approximately equals here. Notice that, again, it was very easy to construct the local linearization. Now what I'm going to do with it, here's my tangent line right here. Now what I'm going to do with it is to take that local linearization, y equals -1 plus 4 times x plus 1, and I'm going to set it equal to 0 and find out where its 0 is, which will be approximately the same as the 0 of f of x. So if I take my local linearization, set it equal to 0, then solve for x, and I can do all of this in my head. I mean, not in my head, I'm doing it on paper here, but still, I can do all of this by hand calculation without having to resort to a calculator, and I get a very good estimate for the 0 of f of x. How good is that estimate? Well, let's go to the calculator and find out. Let's let y equal x cubed plus x plus 1. And we are going to do second calc 0 to find the 0. And it's going to ask us for left bounds and right bounds. And the left bound we already know is -1. And the right bound we already know is 0. And we hit enter. And lo and behold, it gives us a value for the 0, which is -0.6823, which is not terribly far away. It's only 0.07 away from the actual root that we found. So the local linearization then is a powerful tool both for estimating function